Hi from Tokyo, Japan, and welcome to Jeremy's IT Lab. In this video, we'll cover PAgP, Port Aggregation Protocol. PAgP is a Cisco proprietary protocol used to negotiate Ether channels. It was used as the basis for LACP, which is the industry standard equivalent. Modern Cisco switches support both, so you need to learn both. You already know that PAgP uses desirable and auto mode, but in this video, we'll explore some more PAgP-specific information to get you to a CCNP level understanding. Here's what we'll cover. First, we'll review the basics of PAgP as a refresher. We'll then take a look at some packet captures of PAgP messages and see their contents. Next, we'll look at the different timers that control PAgP. Finally, we'll cover a few specific configurations: the learn method, port priority, and silent and non-silent modes. Let's get started. First, let's cover some basic information about PAgP, including some details we didn't cover in the last video. Port Aggregation Protocol, PAgP, is a Cisco proprietary protocol that can bundle up to 8 physical ports into one logical port. Since it's Cisco proprietary, it can only work between Cisco switches. In Layer 2 Ether channel, the port channel, the logical port, gets its MAC address from the first physical port in the channel that comes up. If you configure all of the member ports at the same time with interface range, that should be the lowest numbered port. But in Layer 3 Ether channel, the MAC is allocated by the switch as soon as the port channel is created. It's not inherited from a physical port. It uses its own unique MAC address. As you know, you can configure PAgP with channel group mode, followed by either desirable or auto. A port in desirable mode actively sends PAgP messages to negotiate an Ether channel with its neighbor, but a port in auto mode only sends PAgP messages after receiving messages from a neighbor in desirable mode. So if you have two neighbors, both in auto mode, no Ether channel will form. They're both too shy to start a conversation. So if I configure switch 2 in auto mode, it won't send any messages at first. But if I then configure desirable mode on switch 1, switch 1 will start sending PAgP messages. Switch 2 will then reply with its own messages, and they will form an Ether channel. We'll see this when we look at a packet capture soon, but messages are rapidly exchanged during negotiation, and then sent every 30 seconds afterward to maintain the Ether channel. We'll cover the different timers PAgP uses later in the video. PAgP messages are sent to the multicast MAC address 0100-0CCC-CCCC. This is the same address used by CDP, VTP, and DTP. It's one of Cisco's reserved MACs. PAgP uses a SNAP, Subnetwork Access Protocol, protocol ID of hex 0104. I'll point this out when we look at the packet capture. SNAP is an extension to LLC, Logical Link Control. LLC helps identify which Layer 3 protocol is being carried in the Ethernet frame. SNAP extends LLC by including a protocol ID, so less common protocols like PAgP can still be recognized and processed correctly. LLC and SNAP won't show up on the ENCOR exam, so I won't go into detail, but for anyone looking to be a network engineer, they're worth spending some time learning about. Okay, and one more point about PAgP. On a trunk port, PAgP messages are always sent in VLAN 1. The messages may be untagged if VLAN 1 is the native VLAN, or tagged if another VLAN is native. This is true even if VLAN 1 isn't allowed on the trunk. The messages are still sent in VLAN 1, and they will be accepted by the other switch, even if its trunk configurations don't allow VLAN 1. Now let's take a look at a packet capture to see what kinds of information these switches are exchanging. Before looking at the actual contents of the messages, let's look at how switch 1 and switch 2 become neighbors. The messages highlighted in red are from switch 1 in desirable mode, and the messages highlighted in blue are from switch 2 in auto mode. Switch 1 sends the first message, of course, because it's in desirable mode, and then switch 2 starts sending messages in reply. Look at the flags here. Switch 1's first message has a value of hexadecimal 0. There are actually 3 individual flags. The first one is slow hello, which is currently 0 for no. So switch 1 is sending fast hellos. As I said in the last slide, switches rapidly exchange messages to establish the Ether channel. Those are called fast hellos. After establishing the Ether channel, they switch to slow hellos. The second bit in the flags field is the auto mode flag, which tells us whether the port is in auto or desirable mode. The value here is 0, meaning that switch 1 is in desirable mode. The third bit is the consistent state flag. It's set to 0 now, but once both sides are happy with the negotiation settings, they'll set this to 1. In total, the flags field is 3 bits in length, and can be converted to a hex value from 0 to 7. Switch 2's first message has a flags value of 2. That's because its auto mode flag is set to 1, meaning switch 2 is in auto mode. After exchanging a few messages, switch 1 sets its consistent state flag, meaning that it is satisfied with switch 2's settings and is ready to form the ether channel. Switch 2 agrees by setting its consistent state flag too, confirming the ether channel can be formed. Switch 1 then sets its slow hello flag, and so does switch 2. The ether channel is now established, and instead of sending fast hellos, they will switch to slow hellos, sent roughly every 30 seconds to maintain the ether channel. So this part of the exchange uses fast hellos, and this part slow hellos, after the ether channel has been established. We'll look at the fast and slow hello timers more when we cover PAgP's timers next, but for now, let's examine the contents of one of these messages. Here's one of switch 1's messages after the ether channel was established. Within the IEEE 802.3 Ethernet header, there's the LLC header, and here's the snap extension. It includes an organization code, that's an OUI, just like the one found in a MAC address. It also includes a PID, or protocol ID, hex 0104 in this case, which identifies the protocol as PAgP. Since PAgP doesn't have its own ether type, LLC with snap gives it another way to be identified in the frame without a standard ether type. Within the PAgP message itself, here is switch 1's information, and switch 2's information. This is what switch 1 learned from switch 2, and now includes in its messages back to switch 2. At the bottom, you can see there are two TLV fields. TLV stands for type length value, because each of the fields includes a type, indicating what kind of field it is, a length, indicating the size of the field, and then the value is the actual contents. Here are the contents of those two TLVs. The first one is the device name TLV, which carries switch 1's host name. And the second one is the name of the physical port that sent this message. So those are the contents of a PAgP message. Fairly simple. I wouldn't expect any specific questions on the exam about these messages. That said, when studying any protocol, you should always familiarize yourself with the structure and contents of the messages they exchange to understand how the protocol actually works. This is true at the CCNP level, and especially at the CCIE level and beyond. Next, let's look at PAgP's timers, starting with the hello, switching, and interface timers. PAgP uses several timers to control how often messages are sent, how long to keep neighbors in the neighbor table, etc. You can use debug PAgP misc to view debug messages for these timers. I'll show some output as we look at each timer. First is the hello timer, which will appear as PAgP H in debug output. It can be either 1 second, the fast hello timer, or 30 seconds, the slow hello timer. Of course, this timer controls the interval between sending PAgP packets. As I said previously, the fast hello timer is used to establish an ether channel, and the slow hello timer is used afterward to maintain the ether channel. However, you can enable permanent fast hellos with the command PAgP rate fast in interface config mode. Note that if one neighbor is configured to use fast hellos, both will use fast hellos. The slow one will match the fast one's pace. Here's what the configuration looks like in the CLI. Normal is the default, and fast enables permanent fast hellos. This increases the number of PAgP messages that must be transmitted, of course, but also can help the devices more rapidly detect issues with the ether channel. So on modern devices where transmitting PAgP messages isn't such a large burden, I think it's a good idea. Okay, next is the switching timer, called PAgP S in debug output. It's 8 seconds. This timer comes into play when you activate PAgP desirable mode on an interface, but there is no PAgP neighbor connected. If there is no PAgP neighbor, A PAgP-enabled interface will only send fast hellos for the duration of this timer, and after that, it will switch to slow hellos once every 30 seconds. We'll see this in debug output in the next slide. But first, let's cover one more, the interface timer, called PAgP-I in debug output. It's set to 10 seconds. This timer is the interval to wait after activating PAgP and not receiving PAgP messages from a neighbor before giving up on PAgP and enabling the interface. You might have noticed that when you activate PAgP on an interface, it goes down for a bit before coming up again. When you activate PAgP on an interface, it will go down until one of the following. Either it forms an ether channel with a neighbor, or this timer expires. Okay, before checking out other timers, let's see these three in some debug output. To view these timers, I used debug PAgP misc and then activated PAgP desirable mode on switch 1's G00 interface. Currently, PAgP isn't activated on its neighbor, so let's see what happens. Note that I've cleaned up the debug output a bit to only show the output relevant to these timers. I'm also only showing output relevant to the switch's G00 interface, since the output will be the same for G01. First, the hello interval is set to 1000 milliseconds, so 1 second. And then switch 1 starts the three timers for this interface. PAgP-S, the switching timer, is set to 8 seconds, PAgP-H, the hello timer, is set to 1 second, and PAgP-I, the interface timer, is set to 10 seconds. Then, the first hello timer expires, so G00 transmits a PAgP information packet. After sending that packet, the hello timer is set once again to 1 second. And here we get a message saying the interface is down. As I said in the previous slide, when you activate PAgP on an interface, it will go down until either it forms an ether channel, or the interface timer, PAgP-I, expires. The hello timer expires again, so G00 transmits another packet. And it repeats. I've cut out a few hellos to save space, but the process repeats until PAgP-S, the switching timer, expires. Now G00 switches from the fast hello timer, 1 second, to the slow hello timer, 30 seconds. The previous hello timer is still running though, so it transmits another packet before starting the timer at 30 seconds this time. Now G00 will continue to use the slow hello timer for future packets. And a couple of seconds later, PAgP-I, the interface timer, expires. So finally, G00 comes up, unable to form an ether channel. So to summarize, here we have the three timers being set. Then there is a series of fast hellos. The switching timer expires, so G00 switches to slow hellos, and then the interface timer expires, so the interface is enabled. In addition to these debugs, there is a PAgP-specific show command that you can use to verify that these timers are active. That command is show PAgP internal. It shows information about the local device's PAgP-enabled ports. If you use the command right after enabling PAgP on a port, you'll see the hello, switching, and interface timers are active. The H, S, and I timers are all listed in the timers column. Keep issuing the command, and 8 seconds later, you'll see the switching timer is disabled. Now only the H and I timers are listed. Also, the hello interval has now changed to 30 seconds. 2 seconds later, and now only the hello timer is active, and the hello interval remains 30 seconds. So those are the hello, switching, and interface timers. But there is one more timer listed in this output, the quit timer. Let's take a look at that timer and one more. The last two timers we'll cover are the quit timer and the partner timer. The quit timer is more of a counter than a timer. It's 7 messages. In debug messages, it's called PAgP-Q. It's only used by ports in auto mode. It's the interval to wait after ceasing to receive PAgP messages from a neighbor before halting the transmission of PAgP packets. As you know, ports in auto mode only send PAgP messages if they receive messages from a neighbor. Well, if that neighbor stops sending PAgP messages, the port in auto mode will only continue sending messages for the duration of this counter. The counter is reset each time the port receives a PAgP message from its neighbor. and if the counter expires, the port reverts back to passively waiting for PAgP messages. Here's a packet capture demonstrating. At the top, we have the last message from switch 1 to switch 2. After that, switch 2 sends 7 messages and then stops. It reverts back to passively waiting for more PAgP messages. So that's the quit timer. Next, the partner timer, PAgP P in debug messages. It's 3.5 times the hello timer. So that's 3.5 seconds for fast hellos, which are 1 second, and 105 seconds for slow hellos, which are 30 seconds. This timer is used in both auto and desirable mode, and you can think of it like the OSPF dead timer. It's the interval after receiving the last PAgP message from a neighbor, also called a partner, before giving up on that neighbor and removing it. Like the quit timer, this timer is reset each time the port receives a PAgP message. It's not obvious, but you can actually see the effects of the partner timer in the packet capture above. Here it is once more. Of the final 7 messages that switch 2 sent, notice that the first 5 are all roughly 30 seconds apart. That's because switch 2 is maintaining switch 1 in its neighbor table and continues sending slow hellos. But then the partner timer expires and switch 2 gives up on switch 1, removing switch 1 from the neighbor table. So switch 2 reverts to sending fast hellos for the final messages. They're about 1 second apart. Let's look at that process again in a debug to see the quit and partner timers. Here's a message indicating switch 2 received a message from switch 1. This is the final message from switch 1 to switch 2. Since switch 2 received a message from its neighbor, it resets the quit and partner timers. The partner timer and all of the previous timers we saw are displayed in milliseconds. The quit timer says 7, but that doesn't mean 7 milliseconds. That's a bit too short. As I said in the previous slide, this means 7 messages. After switch 1 stops sending messages to switch 2, switch 2 will send 7 more PAgP messages before it stops. Here's one of them. The hello timer expires, so G00 transmits an information packet, and then the hello timer starts again with a timer of 30 seconds. This continues for a bit, but as I've highlighted here, switch 2 is realizing that it's not receiving PAgP messages on G00. At this point, switch 2 stops the partner timer and clears the neighbor, switch 1. It then switches the hello timer from 30 seconds back to 1 second, and sends a few more hello messages. Finally, it stops the quit timer, as well as the hello timer. So it's back to passively waiting for messages from switch 1. Okay, those are the PAgP timers we'll cover in this video. Hello, switching, interface, quit, and partner. We could spend a lot of time examining all of these timers in greater detail, but then we're diving more into the CCIE level. However, I do recommend experimenting in a lab. Activate the debugs and analyze the output. For example, what happens if one partner uses default hello settings and the other partner is configured to use fast hellos? And how does that affect the partner timer? And if you look around in the CLI, you'll find the command PAgP timer. What does that command do? Asking questions like that and verifying them for yourself is a key skill for CCNP studies and beyond. Next, let's look at the PAgP learn method. The learn method is an interface level setting that exists for interoperability with older devices. You can configure it with the command PAgP learn method in interface config mode. The two options are aggregation port and physical port. This controls how the switch learns MAC addresses from frames received on Ether channel member ports. Aggregation port, which is the default setting, means that MAC addresses are learned on the port channel interface, not the member port that received the frame. Forwarding is then handled by the Ether channel's load balancing algorithm, which chooses a physical port to send each frame. So if switch 2 forwards these two frames to switch 1, and switch 1 receives one on G00 and the other on G01, switch 1 will learn both frames' MAC addresses on the port channel, PO1. The physical port that received each frame doesn't matter. The MAC addresses are associated with the logical port channel. With the physical port option, MAC addresses are learned on the member port that received the frame. This means that frames destined for the learned address will be forwarded out of the port on which the address was learned. So, using the same example, switch 1's MAC table now records each MAC on the specific port it arrived on. Each MAC address is associated with the port that received the frame. However, here's the key thing. Modern Cisco switches only support aggregate learning, but the command remains in modern iOS. To see why this option still exists, let's take a look at what Cisco's documentation says. Here's an excerpt from the Layer 2 configuration guide for iOS XE version 17.16, specifically for Catalyst 9300 switches. The device supports address learning only on aggregate ports, even though the physical port keyword is provided in the CLI. The PAgP learn method command and the PAgP port priority command, that's another command we'll cover, have no effect on the device hardware, but they are required for PAgP interoperability with devices that only support address learning by physical ports, such as the Catalyst 1900 switch. That's a pretty old switch model, but Cisco is big on backward compatibility. They want newer gear to still work with legacy devices. When the link partner of the device is a physical learner, we recommend that you configure the device as a physical port learner by using the PAgP learn method physical port interface configuration command. Set the load distribution method based on the source MAC address by using the port channel load balance source MAC global configuration command. The device then sends packets to the physical learner using the same port in the ether channel from which it learned the source address. Only use the PAgP learn method command in this situation. So this is a setting you're probably not going to use in most modern networks, but it's still in the CLI and Cisco mentions it in their documentation, so it's worth knowing about. Let's verify in the CLI. Even when you're reading Cisco's official documentation, it's always good to verify things yourself in the CLI. I enabled physical learning on switch 2's ports with PAgP learn method physical port. You can verify with show PAgP internal. Notice that the learn method is listed as physical in this output. And on switch 1, you can verify with show PAgP neighbor. I've highlighted each of the flags. Switch 2's ports have all 4. The S flag means switch 2 is sending slow hellos. The A flag means switch 2's ports are in auto mode. The C flag means consistent state. In other words, the switch's settings are consistent and they have formed an ether channel. And the P flag means that switch 2 is using physical port learning, not aggregate. At first glance, this might seem to contradict what the Cisco docs say. It seems that switch 2 is using physical port learning. Let's verify further by connecting two PCs and sending some traffic between them. When we check switch 2's MAC address table, we can see that it's actually learning MAC addresses on the port channel, not the physical ports. So by using the command PAgP learn method physical port, you're telling the switch to advertise to its neighbor that it uses physical port learning, even though it doesn't really. As I said before, modern Cisco switches only support aggregate learning. Now let's look at the port priority. It was mentioned in the previous Cisco quote about the learn method. Like the learn method, it's another interface level setting that is no longer supported on modern devices. Let's take a look at what it was originally used for from the same configuration guide. You can also configure a single port within the group for all transmissions and use other ports for hot standby. The unused ports in the group can be swapped into operation in just a few seconds if the selected single port loses hardware signal detection. You can configure which port is always selected for packet transmission by changing its priority with the PAgP port priority interface configuration command. The higher the priority, the more likely that the port will be selected. This feature seems a little odd to me, since it defeats the point of bundling. Only one port is active at a time. Perhaps that's why they removed support for it, but let's check it out in the CLI. You can configure the port priority from 0 to 255. As the above quote says, higher means the port is more likely to be selected. Here, I've configured switch 1's G00 with a priority of 255. You can verify that the priority has changed with show PAgP internal. G00's priority is 255, and G01s is the default of 128. But just like in the learning method example, this has no actual effect on the switch. Here's that quote again. The PAgP learn method command and the PAgP port priority command have no effect on the device hardware. These options still exist in iOS and are mentioned in the docs, but they're really just there for backward compatibility. So it's good to know about them, but you're unlikely to use them in modern networks. And now we move on to the final topic, silent mode and non-silent mode. In making this video, I spent more time than I'd like to admit in trying to verify how these modes work. Let's get into it. Cisco documentation mentions two additional PAgP submodes, silent and non-silent. These are submodes of desirable and auto mode. The ENCOR OCG, official cert guide, which is published by Cisco Press, also mentions them. And there is no mention of them being legacy features, unlike the learn method and port priority. That said, these two submodes don't seem to have any effect in modern Cisco iOS. The configuration commands still exist, however. When configuring a port in PAgP desirable or auto mode, you can optionally add the non-silent keyword, and it says start negotiation only after data packets received. The default is silent, so there is no keyword for silent mode. Let's see what Cisco's docs have to say about it. If your switch is connected to a partner that is PAgP capable, you can configure the switch port for non-silent operation by using the non-silent keyword. If you do not specify non-silent with the auto or desirable mode, silent mode is assumed. Use the silent mode when the switch is connected to a device that is not PAgP capable and seldom, if ever, sends packets. An example of a silent partner is a file server or a packet analyzer that is not generating traffic. In this case, running PAgP on a physical port that is connected to a silent partner prevents that switch port from ever becoming operational. However, the silent setting allows PAgP to operate, to attach the port to a channel group, and to use the port for transmission. So that's what the documentation says, but it seems to be incorrect. First, let's address this statement. If you do not specify non-silent with the auto or desirable mode, silent mode is assumed. It's the default. Let's verify in the CLI using debug PAgP event. On switch 1's interfaces, I use channel group 1 mode desirable non-silent, and the debug says that PAgP is enabled with mode desirable non-silent. Okay, as expected. Next, remove that configuration, and then configure channel group 1 mode desirable without the non-silent keyword. Note how it still says it's enabling desirable non-silent mode, even though silent mode is supposed to be the default. Let's remove that command and move on. I then configured channel group 1 mode auto non-silent, and the debug says auto non-silent mode. Let's remove that command and do one more. Last is channel group 1 mode auto without the non-silent keyword, and the debug says it's enabling auto silent mode. So what does all of this output mean? First, desirable mode has no silent submode. It's in non-silent mode, regardless of which command you use. And this sentence from the documentation should change to, if you do not specify non-silent with auto mode, silent mode is assumed, because it's not true of desirable mode. As you see here, desirable is always non-silent. After doing lots of tests and finding no difference between auto silent and auto non-silent mode, I found this post from Peter Paluk, who is a Cisco employee and a true expert in the field of networking, which I'm not yet. I'm not going to read the post, but feel free to pause the video if you want. None of the other explanations I found online or in books match the results I've gotten from all of the testing I've done. The reason I chose to mention this topic in this video is because it's in the Cisco documentation and it's in the official cert guide, which many of you are probably using to study. I honestly wouldn't expect any questions about it on the exam, but just be aware that it doesn't seem to do what the documentation says it does. Maybe it did in the past, but not anymore. Here's a one-slide summary of some of the key points in this video. Port Aggregation Protocol, PAgP, is a Cisco proprietary protocol that can bundle up to 8 physical ports into one logical port. It can be configured in interface config mode with the command channel group, the port channel number, mode, and then desirable or auto. Note the optional non-silent keyword. As we just covered, this doesn't seem to affect how PAgP actually operates. I used these two show commands a few times in this video: show PAgP internal and show PAgP neighbor. They're useful commands in addition to the standard show ether channel summary when verifying and troubleshooting PAgP ether channels. Devices using PAgP send messages to the multicast MAC address 0100-0CCC-CCCC, which is also used by CDP, VTP, and DTP. We covered some timers that PAgP uses. First is the hello timer, which is either 1 second for fast hellos or 30 seconds for slow hellos. This is the interval between sending packets. By default, switches will send fast hellos at first and then switch to slow hellos, but you can use the command PAgP rate fast to enable permanent fast hellos. Then we configure the switching timer, which is 8 seconds. How it works is, if there is no PAgP neighbor, a PAgP-enabled interface will only send fast hellos for the duration of this timer. It will then switch to slow hellos. Next is the interface timer, which is 10 seconds. This is the interval to wait after activating PAgP and not receiving PAgP messages from a neighbor before enabling the interface. If there is a neighbor and they form an ether channel, then this timer is skipped and the interface comes up as soon as the ether channel is formed. Then we looked at the quit timer, which is more of a counter than a timer. It's 7 messages. It's used only in auto mode, and it's the interval to wait after ceasing to receive PAgP messages from a neighbor before halting the transmission of PAgP packets. In other words, the port reverts back to passively waiting for messages. The final timer we covered is the partner timer, which is 3.5 times whatever hello timer is being used. It's used in both auto and desirable mode, and it's like the OSPF dead timer. It's the interval after receiving the last PAgP message from a neighbor, before giving up on that neighbor and removing the neighbor from the table. Okay, those are the timers we covered. We then covered a few features that don't actually have an effect on modern devices, although they are configurable. The PAgP learn method and port priority are 2 interface level settings that exist for interoperability with older devices. Here are the commands to configure them. If you modify them, the device will include the modified values in the messages it sends to its neighbor, but they won't actually have an effect on the device. We also cover the silent and non-silent submodes, which are a bit of a mystery to myself and others who know a lot more than me. Ports in desirable mode are always in non-silent mode, as we saw in the debug output. Ports in auto mode can be configured in silent mode, which is the default, or non-silent mode, but it doesn't appear to have an effect either way. Okay, that's what we covered in this video. Now let's do a short quiz to test your understanding. Here's quiz question 1. Examine the output. Which of the following statements are true? Select 2. Pause the video now to think about your answers. Okay, the answers are B and D. This example shows the output of PAgP neighbor on switch 1, so the output is about its neighbor, switch 2. The A flag means that switch 2's ports are in auto mode. If switch 1's ports were also in auto mode, they wouldn't become neighbors, so B is correct. Switch 1's ports are in desirable mode. That also means option A is incorrect. And the P flag means that physical port learning is enabled on switch 2, using the command PAgP learn method physical port. On modern devices, that doesn't actually affect how switch 2 operates, but it means the command was configured. C is incorrect because switch 2 has the S flag, meaning it is sending slow hellos. So fast hellos were not configured. And E is incorrect because we can see the C flag, meaning consistent state. This basically means that the switches have approved of each other's settings and formed the ether channel. Okay, let's go to the next question. Here's quiz question 2. A debug shows the output below. Which of the following statements are true? Select 2. Pause the video now to think about your answers. Okay, the answers are A and D. The PAgP queue timer is the quit timer, which controls how long the port will continue sending PAgP messages after ceasing to receive PAgP messages. So D is correct. This timer is only used in auto mode, because ports in desirable mode will continue sending messages regardless. So A is correct, and B is incorrect. Option C refers to the switching timer, PAgP-S in debugs. And option E refers to the partner timer, PAgP-P in debugs. In this packet capture, you can see the quit timer in action. After switch 2 stops receiving messages from switch 1, it sends 7 messages and then stops. Okay, that's all for the quiz. And that's all for this video on PAgP. PAgP is the original Ether channel negotiation protocol, but to be honest, these days LACP is usually the preferred choice for its multi-vendor support and ability to bundle up to 16 ports, with 8 active ports and up to 8 standby ports. In fact, if you look at the CCIE Enterprise Infrastructure exam topics, they mention Ether channel, but only static and LACP, no PAgP. But with that said, PAgP is still in use in many networks. Anyway, I hope this video was helpful to deepen your understanding of how PAgP works. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members who support me through YouTube channel membership. To become a member, please click the Join button under the video. Thanks to George, Gustavo Macedo, Marcel Lord, Dragos Hernea, Zakib Shah, Mayor Salman, Bold1C1U, Mark Jackson, Gerald Guillaume, Hector Hernandez, Arpad Conives, 5 Feet, Owad, Hussein Yavuz, Samuel Tavares, Kevin Hayes, Brian Grant, Georgi Gemejev, Adelson Pereira, Madmark 50484, Alexandru Stratan, DMJ2, Steve Cox, Jasper Yim, Pedro Hartman, Tricky Mickey 123456, Jefferson Steelflex, Toxic, Sinan Sarisinar, Wilmer Romero, Daniel Andrade, Dragos George, Philip Jovanovic, Sunny Idigu, Mike Crumby, Hello BPDU, Mikhail Chapsky, Hemanth Jabalpuri, Dariush D, Juan Morales, Gonzalo Nicolas, Doomed Soul, Julio Maya, Egreso, Anand Abiankar, Clyde Mkorobindo, Orlando Flores, Adrian Martinez, GG7, Tobe Hedin, Ray Enriquez, MD Danielwitz, MDS Electron Arzedja, G. Gant, Henrietta Sauer, Yukshika, Uma Shankar Sharma, Aliriza Bilir, Sebzi, James Corley, Oleksiy Usov, Excelius, To Be Like Our Superheroes, Mohamed Balta, Tazo Gurganadze, Brandon Byers, Opsero, Mohamed, Mateo Falcone, Omole Celine, Genre Be Good, Zach Ross, I'm Me 87, KB Marco, Christ Ready Adventures Limited, DB Foreigner, Thug Life, Modi, and Manolo Esquivel Villanueva. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.